Okay, we're recording now. So, what are we doing? Right now, we're going to do a summary of the whole course. Now, when I say summary, I'm going to try to give it to you in chad hamachta, as they say in the Gemara, nishima chad, or in one miksha chad. We're going to start from the beginning of the course all the way to the end of the course. The purpose of this is for you to be able to, first of all, hear all what we've done, and we've done a lot during this course, and for you to identify those elements that you feel good about, that you, okay, and also to identify those things that you want to be able to review afterwards. And again, this is another way of reviewing the material. I'm trying to review the material in different formats. So this format is using the summary. And why did I say take a pencil and paper or pen and paper? Write down. When you hear something that you're not clear about, or whatever, write it down for you to investigate afterwards. Every single slide, most of the slides are from all the different slides of the course. And every slide has a number. This is a separate summary presentation. And what it will also, this actual presentation will be in the Moodle as well, just as the PowerPoint, and of course on the YouTube. And the idea is for you to be able to write down the number of the slide. Okay, he said something I didn't understand, go back to it. And we have a big advantage this year, actually, is that it's also being recorded. So you can always go back to the recording and listen to it. And listen to it this way or that way. Now, I'll be talking relatively quickly, because especially if we're recording it, then it's not a problem for you afterwards to listen to it slower or faster, even if I'm not talking quick enough for you, just like in all the different videos. No questions. There's no reason for questions at all. We're not going to answer any questions. I won't be looking at the chat. I'm telling you now, I won't be looking at the chat as I won't be looking at the chat because I won't be distracted. I'm going to be a bit further away, even so you can see me. And the idea is for you guys to sort of see what's doing who's what. So
you cannot ask questions?
No questions. You want to ask a question now before we start? Yes.
No, but I'm sure I'll have a lot on the way.
Okay, so the idea is a lot of questions will come up. You'll have a lot of questions to yourself. Definitely, you'll have questions. So part of the thing is for you to try to solve it yourself. The easiest thing is to ask me questions. That's not always the best way. Try to, by yourself, try to find answer. If not, you can definitely, I answer, as you know, in the emails, not a problem. Also talk between yourselves, it's not a problem. But in the first instance, try yourself to try to get an answer. If something's not clear, you can also write to me. You can write in the chat if you want, and I'll see that. I can go through the chat afterwards to see if there's something major that I can deal with while we're talking, and while afterwards I can write to everybody. Okay, so after that introduction, we're going to be starting. Is everybody ready? Good, I'm starting. So when we talked about this course, hello, why isn't he working? Whoopa, 1 minute. Sorry, guys. This is supposed to be working. Yeah. 1 minute. Okay, and as usual, during this time, we are going to start how we usually do. וישבח אבותינו ואמותינו אברהם, יצחק ויעקב, שרה, רבקה, רחל ולאה. הוא יברך וירפא את כל חולינו, וביניהם הזקוקים לרפואה שלמה. בעבור שאנחנו מתפללים להחלמתם, בשכר זה הקדוש ברוך הוא ימלא רחמים עליהם, להחלימם ולרפאותם ולהחזיקם ולהחיותם. וישלח להם מאירה רפואה שלמה מן השמיים, עם כל חולי ישראל, רפואת הנפש ורפואת הגוף, השתה בעגלה ובזמן קריב, ונאמר להם. Now, we're going to start now Now, how did we start? Actually, everybody here in this course, what you did is you came with everybody came with their own toolbox. The toolbox that you had from the first semester. During the first semester, you had, you learned certain tools. Some of you, this is the second time you're learning the course, and you have rust on it. Some of the things maybe even still in the packaging. And what happened is that during the course, we added more and more things into this tool chest. And the idea of the course is that you're given a problem, you're given you want to build an application, an algorithm, and you have to choose which of these tools or a mix of tools to be able to come to the solution. And in this course, we added many, many more tools over and above what you learned in the previous course. As we started off with the idea of an algorithm. We start an algorithm, and that's the whole basis to the whole course, is algorithms. And not only the design of the algorithm, we're talking about also how we look at them. So what did we do? We had two major aspects that we had to take into account. The first thing is the correctness. Your algorithm has to be correct. Your algorithm has to be correct. No question. It has to be correct for every input. Which is correct, that we defined. We defined a certain type of, that the input is, for example, we could say they're all positive numbers. So if I'm given positive numbers, then I guarantee that my algorithm will be correct. NFS, it has to be correct. You give me incorrect input, then I'm not responsible. Just for example, we talk about a stack. We talk about the method of pop. Okay, so if I said my pop assumes that your stack, that when you call pop, that it is non-empty, that the stack is non-empty, okay, fine, then it will work. But if you send me an empty stack, then I'm not responsible for the problem. I can define my algorithm that it will deal with it. Okay, fine. Depending on how you define it, then my algorithm has to be correct. And that's something that you already saw in the first semester. In this semester, we added another thing. We added also look at the efficiency. Not only that our algorithm has to be correct, we want it to be as efficient as possible. There is optimization, but we also want to make it sure that it's efficient. And we started learning different ways of looking at efficiency. Yofi. So what did we do? We did the following. We started saying, okay, how do you measure Bechlal efficiency? So we saw that there were two main ways of looking at it. We saw that there's time and space, meaning how long does it take, or how much memory does it take? Now, the idea of how much memory does it take is an important concept, because it could be that I'm building some type of algorithm which is built on some type of machine. I don't have a lot of memory on it, and how much time? It could be exactly the reverse. That it's very important for me, the time constraints, and you know what, I can take up extra memory. And this balance between time and space is something that we deal with when we're building our algorithm. In this course, most of the time we talked about time efficiency. We did look at different things about space. Later on in more advanced courses, you'll be seeing also different ways of proving space and stuff like that as well. But here, we did look at certain elements of space, especially when you're designing your own data structure, defining your own abstract data type. That, okay, yes, we can also look at the space constraints as well. Okay, so what happens? We started seeing, okay, how do you check the complexity? How do you compare the different things? And we saw all different aspects. Again, I'm telling you now, a lot of the slides, I'm just going to run through them, but they're here for you, that they're on Moodle site, and you can say, okay, number 7, this thing is going to drive everybody crazy, and you can just write it down. Okay, number 7, you can look at it later as well. Okay, so we saw all different elements. How? Okay, so what happens? How do we compare? We compare by 2 different ways. We can talk about improvement by a constant. We saw that, okay, we can run this with 2n or 3n or n. Okay, so that we're improving by a constant. But we saw also the idea that we can compare by an order of magnitude. I can compare by an order of magnitude, and what's that give me? Comparing by an order of magnitude, and then it's totally different. For example, if I compare merge sort to bubble sort, that's n log n, that's n squared. That's a really difference of order of magnitude. Binary search versus sequential search, log n versus n, and that's a totally different ball game. So we saw that we have an algorithm. You can build many algorithms for the same problem. And then we can see, okay, as it says in the Mishnah, ki yikare algorithm lefanecha, we can start looking at it. Is it better or not? Whatever. But the idea is that we can solve it in different ways. And there are problems. Well, we know the solution, but the solution is not, it's not reasonable. We saw the idea of an algorithm runs in n factorial time. We know the solution, but the runtime won't be reasonable. But we're talking, obviously, in this course on those type of algorithms which are reasonable. And then we saw the idea, the concept of pseudocode. What's the idea of pseudocode? Pseudocode means that we're not writing for a certain implementation in a certain computer or a certain language. We're just running pseudocode. We'll say return. Okay, when I say return, what am I returning? I'll say return error. How are you returning that error? If it's in C++, I'll throw an exception. I want to look at at a node. Is it a pointer? Not every language has asterisks, node kochavit, as they say, node star. Not every language has pointers like that. It's not. When I go to implement it, I'll implement it. But I can write algorithm in pseudocode in a more general form. And then when I get to the actual language, I'll write it. Arrays in this course, again, I remind you, are starting from 1. The index starts from 1, except if we say otherwise. I can't start arrays at a different index. I can start from 0 if I say so. But the default value for starting arrays is 1. Yofi. So then we talked about runtime. A runtime of the algorithm. The runtime of the algorithm, Rabotai, means that we're talking about, maybe this will work better. Yes, good. This will be better, sorry. When we're talking about a runtime of an algorithm, when we're talking about a runtime algorithm, we're talking the actual time that it runs. That's when we say, let's do a function, let's take the runtime of a function. So here we can say t of n, the time that n runs is C0. That is this command here, I is equal to 0. That's running at a constant, some type of constant time. And then we have a loop here, n times. What am I doing n times? I'm going to do some type of command that runs in O of 1. And that's how I get that function that we talk about. Okay, here is a runtime, here is the function, the runtime of an algorithm. Is it omega, is it O, whatever, but where did we get it from? We talked about the runtime. Now, most of the questions at our level of the course, we're not dealing with computing or looking at the actual runtime. That's maybe more advanced class courses, especially in recursion, you'll be dealing with that a lot. But this is how we get to these functions, and we say, okay, the function is 3n plus n squared. How did we get to that? Because we looked at the actual algorithm. Yofi. So now, we said that there are 3 different things that we have to think about. We have to think about the worst case environment. But I have, we're always going to talk about the input size. But everything should be a function of the input size. Usually, we call it n. Usually we'll call it n, which is the amount of elements in the array or in the tree or in the heap or in whatever data structure we're dealing with. But sometimes it could be the number of digits, just like in Heap Sort. In Heap Sort, what did we see? We saw that we had the number of digits, that is the input size. So we always have to identify what is the input size. It could be there's two different input sizes. I'm merging two arrays, one in size n and one in size m. So I have n and m. Okay, they're both linear, but there's two different sizes. And we saw a lot of times that we have to take that into account while we're dealing with it. So if we have an input size of n, and I have my function n, which runs at a certain runtime. So we have the worst case scenario. In the worst case, because the elements are certain types of thing, the algorithm will work in a certain time. We also have the best case, that the same algorithm, the same code will run in a best case environment, that if in certain, let's take the example of sorting. So if I take insertion sort in the best case will run in O of n. And in the worst case, it's n squared. So we saw this idea, that the concept of worst case and best case. And the average case is, some type of case is not the best, but it's not the worst. So we saw that a lot of times we want to differentiate between these different cases. And when we look at the complexity, then definitely we want to look at these different cases. And then we started looking a bit of maths, right? Okay, what's the order of magnitude? Now this is mathematics, right? Okay, we have a constant with log n squared, n factorial, n to the power of n, which is even the worse. Now, one thing that might be very good for you is this. This gives you a nice who's bigger, who's smaller. For those type of questions like we saw last week, the question from exam from 2 years ago, here's a list of things and put them in order. And this type of thing can really help you. Again, if it's an open book test, that's even better. But this gives you the idea of order of magnitudes, who's before who. Okay, so in slide 16, you have how we're looking at efficiency. We have to know what is the size. I remind you, we're talking about n. The size, the input size, is shoef to infinity, meaning we're assuming that it's going towards infinity. We're not talking about small numbers of n. It could be that if I compare two different algorithms, 50n, that runs at 50n to n squared, nachon, that if n is equal to 5, n squared is going to be quicker. But we're not talking about that. We're talking about in a more general fashion. We're talking about with a large n, then the order of magnitudes does come into play. But we're not, so therefore, we're not talking about a specific case, well, if n is equal to 2, you're wrong. No, not wrong. The n, we're talking about large n's. And of course, we saw that a constant 5n and n, from our point of view, is the same thing. And then we started seeing the whole idea of asymptotic notation. The asymptotic notation is a way for us to talk about the function. How does it relate? So the whole idea of a big O means that there is some type of function that for a C, for a C, there is a C and an N0, that C times Gn, for any n from a certain point where n is greater than or equal to this n0, from this point on, the f of n is bounded from above. We're talking about an upper asymptotic bound. That means it's not going to be more than g shall n. When I say O of n squared, it's not going to run, the runtime is not going to be more than n squared. It could be less maybe, but it's not going to be more than n squared. It won't be n cubed. Now, obviously, if I write O of n cubed, it's also correct, but we want to try to keep it as tight as possible. And okay, what's the idea? That we want to find some type of constant from a certain point onwards. And you can see visually here from the graph that from the point of n0 onwards, f of n is bounded by the c times gn. It will never go above it. We saw also that we can use limits to be able to prove it. And I want to remind you, if the question says prove formally, you have to use this type of idea of f of n is less than equal to c times gn. You have to use that. If it's just says prove or refute, then you can just use the limits to prove what you want. Okay, that's also doable. So we saw big O. Then we saw the idea, the same idea, but from the bottom, for the big omega. Big omega means the same idea, but f of n is larger. From that point n0, from that point onwards, f of n is always bounded by this, it can never be lower than g shall n, meaning that it's always, it will it can never run better than the g shall n. We saw that when we dealt with sorting, comparison sorts, when we said the delta, the omega of n log n, meaning that the any type of sorting method which is based on comparisons cannot run better in the worst case, can never run better than n log n. But you can't write an algorithm that does it. We'll talk about that a bit further on. But the idea is that this is a lower bound. So obviously, this type of equation or this type of equality is correct. If I'm saying that f of n is bounded, a lower bound by g of n, then obviously g of n is also bounded as an upper bound by f of n. Okay, so we saw that. There are a lot of other different types of equalities like that, but we didn't go into it formally because we didn't need to. But the idea is that one way is the opposite of the other way. And then we saw theta. Theta is basically, we're talking about a tight asymptotic bound. What does that mean? It means that from one point of view, it will never go above something and it will go underneath. So when I say it's theta of n, that means the lower bound and the upper bound are n. It will never go more than n and it will never go less than n. So how did we prove it formally? We said that f of n, we have to choose two constants, c1 and c2. From that same point, n0 and onwards, the function, our function, will be bounded by these two. And then we saw how to do it also using limits. Okay, those were the three main ones, those are the three big ones. Then we saw there were also two small ones, little o and little omega. What's the difference between little o and big O? Is it means that for any positive constant, but it has to be for every particular c, there's always an n0. In big O, we said that we have to find one. We didn't have, but any positive constant, you choose any c, it will work. So therefore, it's a different type of bounding, and we saw the idea that it's not, which is not tight. And with omega, the same idea. Again, any positive, but from underneath. Those were the five, and basically, if we want to look at it, we're talking about the upper bound, the tight bound, and the lower bound. And again, I want to remind you that if you solve a question and say, oh, my C was 2 and N0 was 5. Oh, but I answered it differently. So there, it could work. Nobody says it's not correct. How do you choose each one when you're coming to do a question? That already is when you see the numbers, you see the thing. Well, how it will help me when I want to do some algebraics and I want to deal with inequalities. If I want to divide by something or subtract or do something, then I'll choose numbers which will help me simplify the inequalities. But definitely, there's no one particular answer for a choice. You know, this has to be the C and this has to be the N0. Definitely not. Here you have to look on this slide. You have all the different five, the 3 and the 2, the 5. And how we can use limits to prove it. Okay, so what did we see here? We saw the whole idea of complexities. And then, so we can start dealing with data structures. Up to now, the first 2 weeks, we dealt with mathematics. Okay, obviously, in relation to algorithms, but it was the mathematics behind complexity, which is very important for us when we're dealing with data structures. Now, when we talked about data structures, we have the whole concept of an abstract data type. It's like a class. What's an abstract data type? I can say, okay, what are the attributes and what are the methods that I'm going to do on it? A stack. Okay, the stack. I can put in a key, I can put in integers, and I can do these commands, pop, push, everything. Now that's abstract. When I go to implement it as a data structure, I'm going to implement it as a data structure, Then I have all the different considerations of implementation. But I can say push and pop. How am I going to implement it? If I'm going to use an array, I'm going to use a single linked list, whatever. But that's already an implementation level. But I can write my code, I can write my main, and say push, pop. You can change the implementation, and my main will still work. I'll say push, I'll say pop. It could be that the complexity will be different if I'm using this type of implementation or a different type of implementation. But we're building abstract data types, and you can build, and you build on existing ones. I can build something which uses 2 or 3. I can build, for example, I gave an example to somebody before class. I can build a tree that each node in the tree contains a stack. Why not? If that helps me solve the solution, solves the problem that I want to deal with, I can have every node has a stack, contains a stack of things, or a queue, right? Why not? You can build your own empires here. You build your own abstract. Then you go tachlis and you use existing things to be able to, the primitive types, to be able to build your abstract data type. So that's what we saw when we're dealing with data structures. So we started seeing different types of data structures. The first ones we saw were linear data structures. We saw 3 main linear data structures. The first basic one is called a linked list. A single linked list. The main element is a node, right? Or link, an element, and it contains always, we can talk about the key, the data that we want to. Now that data can be just an integer or it can be a whole object. I don't know what. But that's the data. And then he knows who the next one is. The whole idea is in a linked list, each element knows who's the next one in the list. Therefore, if I'm looking now in C++, and this is just an example to show you, to explain a bit more. Again, this is implementation. My node in C++ will have the info, which is, or key, those are both of the same words that we use, and of what's called of info type, whatever the info type may be. You might template it if you're using C++, fine, I'm not worried about that. And the next is a pointer to the next node. That's in C++. But I can say next. Next is the attribute. And I can talk about next of X, or Z here, Z dot next, or the next of Z, depending how I write it. So what do I have? I have each one points to the next one. How does my tree, my whole list, how does it look? Sachakol, I need to know the head. I need to know who the beginning is. Where is the beginning of this list? So we have something called head, which points to, head is a pointer to a node. Who's the first one in the list? Great. So we can build our list. And how do I know I got to the end? I have something called null. Null, at the level of pseudocode, null says this is the end. How do I implement that null? If I use null, which is a constant in C++, or if it's I write there -1, I don't know what. I'm not interested. I know I can say if the next of Z is null, It's null. How I implement that in the code is not interesting to us because we're writing in pseudocode. So null is the value that we're going to be using, that we use, null in large and capital letters, says that we came to the end of a list. And therefore I can do a loop while not equal to null, not equal to null. Okay, so we saw the idea of a single linked list. And then we saw, okay, what are the interface? How am I working with this? What is the, in C++, the .h? How do I work with this linked list? So we saw that usually in a data structure, we need the constructor. We want to check if it's empty. We want to be able to insert into it. We want to be able to delete. Usually we want to find some type of element. Those are the basic type of things that we want in any data structure. Then we saw that we had a problem. When we were inserting and deleting, we had a problem because the general insert and delete is fine. It worked. This is O of 1, O of n, whatever, depending on how you do it. But the problem is that if I'm inserting in the first or deleting in the first, I have to deal with the head. So my algorithm becomes a bit more complicated. So one of the ways of doing it is that I'll have a separate dedicated algorithm, insert first or delete first. I could, in my insert, have a whole block of an if and say, if the head is the first one, and then start doing a whole separate coding for it. The easiest way is a separate algorithm, insert first, delete first. Okay, so these are the ways that we can work vis-a-vis the list. I only use these commands. This is my .h, the header file. How you're implementing the insert, the delete, that's for you to do there. Of course, who's you? You also write those implementations, but in general, when I'm talking about using a this data structure, those are the commands that I can use. Okay, so then we saw that the idea is that there's another type of a list which with a centennial, that the first, and we're going to add a dummy element in the beginning. Head will always point to this dummy. So if head is always pointing to this, now if I want to insert in the beginning of the list, logically, the list starts from here. Now, this is where my list is. These are the keys. This one has no key. This is just sort of like a piece of string that's connected to the head. So I can always add after this guy. I can also delete after this guy. So therefore, if insertion and delete, I can use one general algorithm for inserting and deletion. And that was the use of a centennial. We saw also the whole concept of a double linked list. A double linked list means that not only I know who's after me, I know who's before me. Now, what else that help me? That helps me a lot. That if I know, again, and this is, I want to reiterate a very important concept. You have to choose, depending on the algorithm that you're doing, depending on the solution that you want, you choose what is the data structure that's applicable. If you know that you're going to have to be going back and forth all the time in the data, then ding, 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 ding. Oh, maybe double linked list is more appropriate than a single linked list, or more appropriate than even a binary tree or whatever. Depending on how I'm using the data, if I'm doing a lot of inserts with very few deletions, or I'm going to do a lot of searching, and then I'll decide what is the appropriate data structure. So we have now in our arsenal, in our toolbox, this double linked list. We also saw the idea of a concept of a circular list, where the last, the last element of the list points to the first element, not to the head, to the first element. So it's a circular. The head will point to the first, and we can have a circular. Again, when will I use it? Depending on my problem that I'm trying to solve. So that is those types of lists that we saw. Yofi. So after that, we saw, just to sum up, these are the commands and the different types of lists that we have. So in slide 31, you have a summary of everything. Okay. Then we start seeing two different ones, which are basically lists, but they're lists that work in a very, very particular environment. Oh, sorry, before that, we saw that concept, I forgot. We saw the whole idea of a multi-linked list. The concept of a multi-linked list, let's have lists which are multi-linked. So we saw the idea, the concept of a sparse matrix. Now, a sparse matrix is a concept where we know that a sparse matrix is basically defined if up to 10% of the values are at 0, then we'll call it a sparse matrix, because sparse is not a lot, up to 10%. So what we saw, okay, how can we represent a sparse matrix in using lists? So we saw the whole concept of a multi-linked list, basically an array of lists, two arrays of lists, and we stored the information in this type of environment for a sparse matrix. That's what we did. We used the concept of a multi-linked list to represent a sparse matrix. After that, we started seeing two particular cases of lists, which are called stack and queue. A stack is a very, very specific way of going to use the data. If I know that I'm going to use LIFO, last in, first out, means the data, I want to access the data according to LIFO, then a stack is very appropriate. And we saw all the ideas of stack, when we use it, whatever. So what was the commands for a stack? First of all, we want to be able to create one. Constructor is empty, push the value in, pop. Pop was taking out the value on the top of the stack. Again, think about a gun, the bullet in the stack, in your mahsane. And there also was a command called stack top. A lot of times we want to see who's in the top of the stack without taking it out. So we saw there is a command called stack top. Again, the names can be different depending on the book, but the concept is the concept. Now, we have all these commands, and I just want to remind you here maybe is the time to remind you that we can write the commands in two different formats. We can write in the format of more of a functional type of thing, where we'll send the stack and the X, here, pop S, I'll send the stack, or I can use it more in an object type of writing, where I'll write s.push, s.pop, and that's the object that we're dealing with. Again, two different ways of writing it, even at the pseudocode level, and you can write it however is appropriate for you, whatever you feel more natural. In the test, don't mix. In the same question, you have to be ikvi. If you're going to do s.push all the time, and not sometimes this and sometimes that. Different questions you can definitely write in different ways if you need to. Okay. Now we have to think. Okay, that's the concept. How do we implement it? There's different ways of implementing it. Well, again, I'm going to say push. I'm going to say pop. How do you implement it? In the .cpp, I can use an array where I have a pointer, an index in an array called top, and I know who the top is, and I'll put in push and pop comes from the top. I can use a linked list. Now, again, what is the cost? Your stack is going to cost me O of n to delete, to do a pop. Thank you anyway, I'm not interested. But maybe it's better for memory because then it's more agile. Great, thank you very much. Again, you decide when somebody says, look, here's my pop, here's my stack, and this is how it works. It throws exceptions, doesn't throw exceptions. Then you'll decide, the pop costs O of 1, push costs, then you'll decide what to use. Again, there's implementation behind, underneath the hood. Okay, so we saw a stack. Afterwards, we have to think about one very, very important concept. We have a concept called underflow. It could be that my stack is, I'm going to do a pop, and it's empty. And that is going to cause me an error. It's an underflow. There's also maybe a concept of overflow, but there is no concept of overflow at the algorithmic level. My stack is insufficient. It goes on and on, right? Why? Because I'm not implementing it on a certain computer. You can always do another push, continue all the time. When I come to the computer, when I want to implement it, then I might have some type of issues of overflow, because if I define my stack has 100 elements, then I have to check to make sure that I'm not going to overflow. But at the algorithmic level, then definitely I have, I can say pop, push whenever I want. However, pops, I can have a problem even at the algorithmic level because it's empty. So I do have to check if it's empty or not. Then we saw the idea of a queue. The whole idea of a queue was FIFO, first in, first out. And then we're going to have an orderly queue, and the way that we access whoever came first goes out first. Great. Okay, so we saw that. That's very nice. What were the commands we saw? Basically, the constructor is empty. Now we're using here NQ and DQ. Those are the names in this course. Sometimes you'll see Q insert, Q delete. We're using, according to the Chumash of Korman, he uses NQ and DQ, and therefore we're also using it. You'll see sometimes maybe an additional command, just like top, called peek, or look, or see, peek, peek, to peek, peek at something. Q peek, or something called different names, which will also be very similar to top. We'll just say who's at the head of the queue without taking him out. You might see that as well. You can use it as well if you want to, but you just have to decide, just write what does it do. You don't have to implement it at least, but at least say, okay, I have this command if you do need it. Okay, so we have this queue. How do you implement it? We saw a lot of different ways of implementing it. We can implement it with an array. We can do the linked list where the front is here and the rear is here, the rear is here and the front is there. And you know what? Some people call it head and tail, not even rear and front. And each one has its Yitronot and Chesronot. It has its benefits and disadvantages and advantages. And you have even one that the front is chasing the rear all the time, or the rear is chasing the front, some type of circular type of environment. Again, different implementations to a queue, but I say enqueue. Great. And just to emphasize what we talked about, that when I want to build a queue, we saw this exercise. We did this exercise where we said, okay, let's implement the queue using 2 stacks. What's an idea? What's the idea of that? Don't use an array. Don't use a linked list. Don't use a double linked list. Don't use a BST. We haven't learned yet. But the only thing that you can use, the only data structure you can use are 2 stacks. Great, so we saw how to do that. We saw how we can implement. I write in my main enqueue, dequeue. Under the hood, or behind that black door that we talked about with the kiosk. Okay, behind scenes, we'll use 2 stacks and we'll move here and move there and we'll do that to be able to implement enqueue and dequeue. So behind the scenes, we're going to use 2 stacks, not a. So that was the whole concept, the whole idea. Great. Then we stopped. We took a breather. And we started talking about recursion. We went back to what you learned in first semester, in the intro course about recursion, and we went a bit further into the recursion, Yeah, and then we stopped somewhere. Okay, so what is the recursion? We learned a bit of Rambam, okay? And then we started saying, okay, binary search, a recursive binary search. You saw in the first semester binary search. You might have also seen the recursive one, I don't remember. And the whole idea here was, I go into the middle and then go to the left or to the right. And that's a perfect example of a recursive function. Great. And then we saw merge sort. The whole idea of a merge sort, where we say, okay, go to the middle. Well, how does the algorithm look? Look at it. The algorithm Q is equal to L P plus R divided by 2, the floor of it. Let's go to the middle. And then, okay, so Q is the middle point. And then I say, okay, great. Now sort, please, the left-hand side. Sort the right-hand side. When you finish the left-hand side and the right-hand side, sort it. Do the merge. We know how to do merge. And left, right, then merge it all together. I even showed you a cute way of doing this merge using infinity for an extra value. So it optimizes the code, the writing of the code a bit. It was a cute little thing there. But the whole idea is that sort recursively, and the complexity worked out to be n log n. Great. Yofi. So we saw now another one which we knew because you already saw that in the first semester. And then we saw a new one, quicksort. We saw that concept of a quicksort. Quicksort, which is a number 5 in our list of sortings, right? 5th sort that we saw now. Up to now, we've seen 4 sorts: insertion sort, bubble sort, selection sort, and merge sort. And now we see quicksort. What's quicksort say? Quicksort says very simply, let's look at it visually even. Quicksort says, here's my array. Please take A. P is here and R is here. Here are my, I remind you, a lot of times P, Q, R are used for, because of the consecutive letters in the alphabet, to show the lower index, the upper index, and some type of value in between. So basically we say, look, Q will be this. This is Q. How did I get to Q? I called a function called partition, and basically what it does is take. What it does take, it takes a value, a pivot value, which we'll talk about in a minute. It takes that pivot value, which happens to be, in this case, the last value of the array, the 28, and it puts it in its place where it should be. How it does it, hocus pocus. And then the algorithm says very clearly, it says very clearly what to do. What's it say? It says very clearly, what am I supposed to do here? Okay, you put it in its place, and now quicksort all these values, and quicksort the other values. But what are those values? The partition algorithm does something very smart. What it does is make sure that all the values to the left of Q are smaller than that 28, and all the values to its right are larger. That's what partition does. All to the left, all to the right. They're not sorted. And then, okay, fine. So now let's sort the left-hand side, sort the right-hand side. How are we going to do that? Let's use quicksort, which is a recursive function, and we do it. So what's the idea of the partition? The partition, that the choice of that pivot value is very, very important. Now, I remind you, there was a whole, I showed this dynamically. You have it here in slide 49, but if you go to the particular slideshow, the presentation of that class, you can press one button after the other and see it, how it works. But what's the idea? The idea is that I'll take this pivot value. One way, there's basically three different ways you can choose a pivot. Bigadol. There are other ways, but the three main ones are choose the right-hand side, choose the large element, the last element in the array, and that will be your pivot value. You could choose also the first element in the array. There's also a very nice one, which works very lovely, which would be random. Choose one of the values, make him randomly choose one of the values in the array, and he'll be your pivot value. Now, a lot of times, choosing the pivot value is very important for the complexity. If the quicksort is very nice and runs at a great time, okay, this is the algorithm. Here you have the algorithm that really tells us, that shows us how to how it does it. We went into that and how it works. But what is the complexity? The complexity of quicksort was very interesting in that the best case, in average case, it really runs in n log n. What's the best case? That every time it splits equally. The worst case is if the algorithm is already sorted and then my pivot value is always the right-hand side, so everybody is going to be to the left will be smaller and will be nobody to the right. So it will work out to be n squared, and we saw how that comes about. So again, if you're not clear about it, you can go and ayin sham, check what's going on there. But the idea is, in the worst case, quicksort is n squared. However, the expected case of quicksort is n log n, and we expect that. If we know that the numbers are probably can be and could be very much fully sorted, then we won't use the quicksort. But the expected case is n log n, and even more than that, a lot of, just like you have in containers in STL in C++, and a lot of the containers you saw that you have a method called sort. What is the algorithm that's used in the C++ in the STL there, behind the scenes? Quicksort. It's very, very much used because one of the reasons that quicksort is in place. It doesn't use additional memory. Merge sort, as we saw, does use additional memory. So quicksort in our n log n guys, it's great, good. It's in place, and it's also stable. Is it stable? Think about it. Okay. So what do we see? When we talked about recursion, we talked about something called the tail recursion. The tail recursion was type of recursion where the last command in the function is actually that recursive call. Meaning, after I come back from the recursive call, there's not much more. There's nothing to do, and therefore, what will happen is that I'll go all the way back up to the original call from the main, let's call it, to the recursion. There's nothing else to do afterwards. That's a type of recursion, which a lot of times can help us, especially if we're dealing with complexity. Multiple recursion means that the recursive function calls itself more than once. Just like in order or pre-order, we're going to go, okay, do in order to the left, visit the root, and then in order to the right. That is a multiple recursion. And we saw something called co-recursion, where function A calls function B calls function A, and we have to be careful to make sure that we get out of that recursion. When we talk about complexity of recursion, in our course here, we really dealt with it very intuitively. And somebody asked about that. How do I analyze recursive functions? The answer is, in this course, we hardly do that. In data structures 2, you'll be learning master theorem and how to do it and how to really do the analysis. What we do here is intuitively. Okay, I have a tree. I'm going through the tree recursively. I'm going through every node in the tree. Ah, that's O of n. Okay? And that's the type of thing that we do. We can only talk about it recursively. We're not going to prove it formally mathematically, not in this course. So, in every recursive function, you have to have two things. I have to have the base case to get out of it. Otherwise, it's an infinite loop. And what is a recursive function? It's a way of doing an iteration. It's a way of doing something a lot of times instead of using a loop. But then again, I remind you, that question from the homework that we saw was an exam question from 2 years ago in relation to the tree, about how many trees. Don't forget, you can put a loop inside a recursive function. It's not common, but it can be. But the idea is that this recursive function gives me the iteration, do it more and more in a smaller or bigger data set, fine. And then obviously you need that recursive call to be able to be called a recursive function. Okay, all that was basically to be an introduction for a recursive data structure. And then we went to trees. We started talking about trees. The idea of a tree was a very recursive definition. A tree is a very simple definition of a general tree. It's either an empty tree or a root with n subtrees, which are trees. Totally recursive. Great. So then we started seeing all different concepts in relation. What's a parent, a child, a degree? What's a rooted tree? 36 here. Here's 36. That is a tree. I can look at 36 as a tree whose root is 36, because every subtree or left son or right son is a tree in itself. In Hebrew, I'd say it's a etz b'fnei atzmai, or Mishnah terms, right? It's a tree. It's a tree. I can look at each subtree as a tree. So I can say that's its root. We saw the idea of an internal node vis-a-vis a leaf. Any node which has no sons is called a leaf. Sorry, I didn't say that correctly. Every node has sons. A leaf, his sons are empty. They're empty trees. And let's just understand it better. In a minute, we'll understand it better. Then we saw the idea. I'll amplify that in a minute. And we saw the idea of a path, a height. A height is a very, very important concept. It's the length of the longest path from a root all the way to the leaf. The height of a whole tree is the longest one. Okay. And then we saw a binary tree. And then here's the time to explain it more fully what we talked about a definition of a tree. A tree is a root. It's always a root with two subtrees. It always has a root and two subtrees, which each tree, which we'll call left child and right child, because it's two, which are binary trees. That is the definition. Always, every tree, every root has two subtrees, a left and a right. But we also have that a tree, a binary tree, can be called an empty tree, meaning that every node in our tree can have 0 non-empty trees, 1 empty tree, or 2 empty trees. A leaf has 2 empty trees for its subtrees. It's a root. My leaf is a root, and it has 2 subtrees, which are binary trees. Why are they binary trees? Because it's an empty tree. There's no continuation afterwards. So again, every node has always 2 sons. It can be 0 empty trees, 1 empty tree, or 2 empty trees. And this is our recursive definition of a binary tree. And therefore, a lot of our algorithms will be recursive. We saw 2 different types of trees in the beginning. We saw a full binary tree, the whole idea of a full binary tree. And then we saw the idea of a complete binary tree. And those type of definitions are certain types of trees, and we can use them during our course of during the course. Sometimes we go, okay, it's a complete binary tree, therefore, da, 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 da. So these are definitions of trees. Again, you're not sure about it, you don't remember, write down 59, 58, ayin sham. Again, I remind you, that is the purpose of this summary, to show you what we talked about. Then we started talking about, okay, In a complete binary tree, how many nodes are there? So we understood it and we saw how we came about it, that the number of nodes in a complete binary tree with the height is h is 2 to the power of h plus 1 minus 1. This expression is something that we saw a lot in a complete binary tree. Great. And the height, therefore, if I know that I have n nodes, I have n nodes in a binary tree. Again, not BSD, we're not there. We're in a complete binary tree. If I know that I have n nodes, therefore the height will be theta of log n. That will be the height. Now again, that is for a complete binary tree. The height of any binary tree, from one point of view, it's O of n, and the omega is log of n. Means it could be a binary tree, it could be one long line, basically a linked list, right? So the height will be O of n, but I can never do better than log n, right? That will be, log n will be, for any binary tree, I can't do it better than log n. That will be basically a complete binary tree is log n. It's balanced, it's complete. I can't do better than log n. I can't do log n or something like that. But the worst case can be O of n. I can build O of n if it's not complete. That's in any binary tree. Great. Then how did we represent it? And how do we implement this tree? So the whole idea is that my node contains three main elements. The key, again, the data, a pointer to the left and to the right. Again, I remind you, if it's the left is a node, a pointer to a node, or if it's an index in a two-dimensional array, because I decided to implement my binary tree in a two-dimensional array, right? That's how we used to do it before languages with pointers, right? I wrote code using building a binary tree where I had three columns: the key, the index of the left sum, and the index of the right sum. And if the sum was null, empty, it was -1. The index was -1. Great. You can implement it. So again, when you say left and right, again, that's already at the level of the code, how you're going to do it. But in general, when we're talking about the node, we can talk about the key, the left and the right. I have the root of t. The root points just like the head of the list. The root of t points to the root, the head of the root of the whole tree itself. A lot of times, it's very convenient for us to have a parent. Very, very convenient to have a parent. That I have a pointer to the parent. I know who my parent is. Instead of starting to look who points to me to be able to do something, especially deletions or different algorithms as we saw. So if I know that I need to know who the parent is, then I will add it to my, how I'm going to implement my node. But don't forget, insert and delete. I have to update my methods to deal with the parent as well, right? Now, it could be that it's going to be all of one commands, but don't forget that you have to deal with it. With the algorithm, if I have a parent and I'm doing something with it, I have to make sure that I update the parent appropriately. Great. Okay. Now, we wanted to be able to visit. I want to go through all the nodes. I have a tree, and I want to go through all the nodes. I want to do something. I want to check. I want to count, I want to do this, I want to print them, whatever it might be. Now, I want to visit each one. I want to do something in each one only once. I don't want to miss out on anybody. And also, I don't want to do somebody twice. Let's say I want to print. I don't want to print somebody twice. It could be that I'll go through him, but to print him only once. To be able to get to the next side, maybe I'll go through it in the recursion, but I'm only going to do the actual action, which I called here a visit. The actual action will be done only once. We saw there were two different ways of doing it. We could do it through breadth or depth. We can go down or go via levels. So the two different ways of transversal, which were like the Mishnah, Stein, Shen, Arba. What does it mean? We have the depth ones. We had pre-order, in-order, and post-order. The whole idea, where was the algorithm? Didn't put it on here. Should have been. Okay. Pre-order, in-order, post-order. What's that mean? the variation, what's it mean? Let's say take a pre-order. First of all, print it, and then go to the left. You finish the left, do the right. In order, it says, go to the left. You finished on the left? Great, nice. You finished? Print it, and then do the right. How do I know that I finished? How do I get to the bottom? If I'm at a leaf, right? If he has no left sum, and he has no right sum, no left sum, he comes up, and do the left, do this whole left. 17. Okay, let's say I'm doing in order. In order says, take this 17 and do the whole left. Finished? Print, do whatever you want. Then print 17 and do all the right. So we saw the different ways of doing it: pre-order, in order, post-order. The doing it breath-wise, we use an auxiliary queue. How does it work? It was a very, very simple algorithm. It's not recursive. We're going to put the root in the queue, one-time thing, and 3 lines. While the queue is not empty, do a dequeue, take out the value from the queue, print it, and put his 2 sons in the queue if they're not empty. Even better, put his non-empty sons in the queue. That's the whole loop. And then go back, take out the next value from the queue. And because we're using this FIFO environment and we're putting his sons from the left to the right, we're going to get our transversal, and we're going to be able to go through all the values of the tree. We're not going to miss out anybody, and we're not going to print somebody more than once. Great. So those were the ways of transversing. Now, a lot of times we're going to use this basic concept of an in order or pre-order to be able to answer questions. You want to do something, you want to check something. So the basic element is, okay, go left, do something, go right, or do something, go left, go right, or go left, go right, and then do something. You choose depending on your algorithm that you're dealing with. But a lot of the things or questions that we deal with trees is that outlook. That's how we do it. Then we got to a BST. We saw a specific type of a binary tree. This specific type of a binary tree has something very unique. The idea is that when we're dealing with the values in a BST, all the values of my left side, my left side and my right side, my descendants to the left side will be smaller than me. And all my descendants to my right are greater than or equal to. And again, I want to remind you, in this course, and Roiva Oilom says, greater than or equal to the right. That's very important for us especially if we want a stable sort, when we're using a binary sort, using a BST for a binary sort, we want greater than or equal to be to the right, and therefore it will make sure that our sort is stable. So again, to the left are smaller, to the right are greater than or equal to. So we saw what are the operations. We saw we want to be able to insert, to delete, to find. The maximum value and the minimum value of a BST, the minimum value will be all the way to the left. Will be here all the way to the left. The maximum value will be here to the right. Then we saw the idea of a successor and a predecessor. Who's the next one? Who's the successor of 14? According to the values here, in the in-order successor here will be 17. The successor of 14 is 17. Because what was the chiddush here? The chiddush of a BST, if I build a BST, if I go through this tree in order, just like you see here in the example, I get it sorted. Building a BST basically gives me opportunity to get my list in a sorted, my values in a sorted. Okay, so when we saw the successor, we saw that, okay, it was a bit more complicated. We had to look at the algorithm, because who's the successor? It depends if there's a right son or if there isn't a right son. And we saw how it works. Again, you don't remember? Write it down for you, 66. We saw the algorithm, how it works. It was very nice. It's cool how it works. And I know who this successor is. Just like there is a successor, there's also a predecessor. Take that into account. Great. Now, BST, it's very nice, but we want to know what is the height of a BST. Very important for us to know the height of a BST, because I can't define what is the complexity of any type of operation that I do on a BST if I don't know the height. So therefore, we made a very clear distinction. What is the best case, the average case, and the worst case? The worst case of a BST is that it's a linear list, even if it's a zigzag linear list, but big, big, bit smaller, big, big, but it could be a linear list, and therefore the height will be n-1. If I have n nodes, the height itself will be n-1. Great. The best case, it's a complete tree, it's totally balanced, and as we saw, it's going to be the floor of log of n will be the height. Then we saw the average case, and we saw that to be able to build a BST with n nodes, there are n factorial different possibilities how to do it. And then we saw, or even not only saw, I said, I didn't really show all the maths behind it because we didn't really need it. I said you could take it as a lemma, or you can actually go and see how we derived it, that the height is O of log n. Right? I didn't prove that, but it is O of log n. And you can, again, if you're interested, you can see the actual mathematical proof of that. And that is the average case. Okay. Therefore, when we're dealing with BSTs, the average case will be O of log n, my inserts, my deletes. I want to insert into a BST. It's going to be log of n, because that's how I get to it in an average case. And again, in the best case, it will be a which is log of n, the floor of log of n, which is again O of log n. It's still applicable. Okay, so why is that important for us? When we saw how to delete, one of the things that we wanted to see, okay, we saw how to insert. Inserts, okay, go. Take the number, start going left, right, left, right, left, right, until you get down to the bottom, you got to a leaf, add it to the left, add it to the right, we finished. But how do we delete? We differentiated between 3 different cases. When we want to delete, if it's a leaf, pshita, very simple, just get rid of it. Just update the various pointers. If there's a parent, if not, left, right, that's easy. And then if there's only one sum, makes a difference if the right sum or left sum is the same algorithm, okay, deal with it. And we saw also what happens if there's 2 sums. If there's 2 sums, how do I delete the element? How do I deal with it? So we saw how to deal with that. Those are the three different parts to the algorithm you have to take into account. There's 3 scenarios that you have to take into account. Great. So then we saw a beautiful use of the sort. We always said the BST keeps the values in order, it will be sorted. So great. So now we saw a 6th type of sorting called binary sort. Binary sort basically says, okay, create an empty tree, and then do an insert, take AI. Again, I remind you, we're talking about the array. It's called A. We have an array of numbers A, and we want to sort them. So here we're using auxiliary BST. We're going to build this BST, take each value from the array, and do a BST insert. The cost of the BST insert we saw now was log n. And how many times we're going to do that? It's n log n. That's great. But that's in the best case. But in the average case, but in the worst case, it's going to be n squared. Okay? So those are the complexities of a binary sort, depending. So in the average case, then it's n log n. But a worst case scenario can be, what's the worst case scenario? That we're going to get this type of linear list, and therefore it will be, the BST will look just like a linear list, and it will be n squared. Okay. Then we started to roll. Okay, so what did we roll? We learned about how to do rotations. The concept of a rotation. Here I have Q. I have Q. Is it working again? Yes. I have Q. I want to rotate it to the right. If I want to rotate my Q, I'm rotating Q here to the right. So Q comes here. And this one will look. If I want to rotate P to the left, as P goes down here. Now this is a concept of rotation on trees in general. We used it with AVLs, yes. So let's just take a look. So if I take X and I'm rotating it to the left, you know what, let's look at this for a minute. Let's go in order on this tree. I remind you, a triangle like this means a subtree, the whole subtree. It means in order says, do the subtree, A, print out A, left, right, whatever it might be, and then X, and then B, Y, C. That's the in order of this tree. I'm rotating left, I'm doing a left rotate of X, and this is what happens after the rotation. If I go through in order now, A, X, B, Y, C, exactly the same thing, meaning that after the rotation, my in order, it's nice, it stays in order. Okay, so we saw, what's the idea? When we want to rotate, we have basically three values. We have the smallest, the median, and the largest. I called them the grandfather, the father, and the son. This is for this example. Now, what we want to do is we want to make sure that the middle value will be in the middle. The median will be in the middle. So what we're going to do is we're going to rotate the 14th to the left, and we get this. So we're rotating 14 to the left, and we get this value. And the grandfather goes down, the son comes up. Okay. That's the concept of rotations. Now, when we got to AVLs, and I'm keep jumping here, but we're talking about rotations. So we have, and again, I want to remind you the machloket of how we're looking at the concept. We're going to, according to one daya. There is another way of looking at it, but we're going to a way that is much easier to understand and not to get complications and make mistakes, especially during an exam. What am I talking about? I have the matzav, I have the case where, for example, here, I have the left and the left. This value here that I added is to the left of the left. These are the three, and I want to rotate. Right? So from one point of view, you could say the case is a LL, left, left. The rotation, the tikkun that I want to do is a right rotation. A single rotation to the right will make sure that the median is in the middle. Again, the correction is a right rotation. I can't say that the case is a LL, but then you have to remember, oh, the case is LL, but my tikkun is a right rotation. Maybe you can manage with a single rotation, but with a double rotation, where I'm saying the additional is in this left subtree of the right son, I have to do a double rotation. And the correction is doing a right left. And then you can start getting confused. So again, what we're saying now is that you have these four cases, and these are the rotations. It's not the case. These are the rotations that are needed. And I want to remind you, a single rotation, we rotate the grandfather. In a double rotation, first we rotate the parent and get to this type of thing, a straight line, and then we'll rotate the grandparent. Again, double rotation, first rotation is on the parent, and then the second rotation is on the grandparent. Okay, great. So those were rotations. Why did we need all that? Because we wanted to start talking about balanced trees, and we want to use rotations to balance our trees. So we saw the whole idea. If anybody knows this picture, then they know what I'm talking about. We're talking about trees, which are balanced. And that means that the height of these balanced trees belong to the complexity of log n. They're bounded by log n, and they're not going to be higher than log n. So we saw two different types of trees straight away. We saw Fibonacci trees, and we started looking for Fibonacci trees will help us understand. We saw how it helps us to understand with Avl trees, especially in relation to heights and nodes. So we saw Fibonacci trees, Ayin Sham. Okay. Then we saw Avl. And don't forget, first and foremost, an Avl is a BST. It's a BST. Over and above that, it's balanced. We don't have, the heights are balanced. The difference in absolute value between the two heights will never be more than 1. That's the whole idea. We want it to be balanced, and when we add, we want to keep it as balanced as possible. Therefore, we're going to make it the height. We want to minimize the height. So by balancing it, the height will be actually log n. So that's the concept of an AVL, where the balancing factor, it never goes above an absolute value of 1 or minus 1. Absolute value. Okay, so what? How does it help us? What is the height of AVL tree? So we saw the whole, how we proved the height of AVL tree. It's O log n. And basically we saw that the amount of nodes, if you have n nodes, we saw how an AVL tree looks with n nodes. We saw the whole, this is what it looks like. And we can see what's the minimum number of nodes and the maximum number of nodes in an AVL tree. And again, these trees are Fibonacci trees. And that's why we saw the Fibonacci tree beforehand, to be able to understand more completely. In the next slide, you'll see a table that summarizes all the information that we wanted to know about the heights and the nodes. The number of nodes in an AV tree, I have an AVL tree. Its height is h. The maximum is that same number that we know, 2 to the h plus 1 minus 1, because that's a complete tree. A complete tree, we know that's the maximum number of nodes. Again, ayen sham, what we talked about already today. But the minimum number of nodes of a height h is Fibonacci, just like we saw how it looks. It's the number of nodes in a height minus 1 plus height minus 2 plus 1, where NO and N1 are 1 and 2. So that is the number of nodes. What is the height? I have a AVL tree with n nodes. What's its height? Its height is very clear. It's going to be, the minimum number is the floor of log n, again, a complete tree. What is the maximum? And this was a cute number, 1.4 for log n. Where did you get that from? And I explained that this is the golden ratio of them. It's nice mathematical how it works, but in the end result, it's 1.44 log n. That is the maximum number of, the maximum height will be 1.4 log n. Okay, great, so we know all about that. How do we represent a node in the AVL tree? We need the key, the left, the right. We need the parent, very important, the parent, because we need to be able to go up. And we'll keep the height. We need to know what is the height of this tree. At this node, this subtree, what is its height? The BF, again, this is a computed value. You can decide if you want to keep it or not, because what is the BF? It's the height of the left minus the absolute value of the height of the left minus the height of the right. So you can keep it as a value, and therefore you have to update it all the time when you're doing all sorts of rotations and everything, or you can just update the height, and when I need the balance factor, I can just compute it. Again, this way or that way, you can choose. And then we start, okay, how do we do insertion? And we saw all the particular things related to the insertion. One of the important things is that after I did a rotation to correct it, I still have to continue going up all the way to the root and check by my rotation, did it affect the balance factor of ancestors? I have to go all the way back up most of the time, but not always, because going up through the ancestors, and I see that the balance factor of somebody didn't change. One of my ancestors, his balance factor didn't change because of the rotation, then I can stop, because if he didn't change, then obviously there won't be more changes further up in previous generations. Okay, so how does the insert work? So, so that was the concept of insertion, how we do it. Then we started seeing another type of tree, which is the almost complete binary tree, where we're filling up all the time, but the last level, we have leaves, but it's not complete, but from left to right, it's always complete. We're filling it up, but it could be towards the end there isn't. And we saw that that height obviously is going to be also flow of log n, just like with a complete tree. Okay, so how does it affect us? Why is that good? Because we saw the idea of a heap. We saw another data structure called a heap. This heap is a really great guy. Great guy. Great. Why? Why is a heap good? Because first of all, what is it? It's a almost complete binary tree. First of all, it's an almost complete binary tree, so that's the concept. And what we know is that every node, and here I'm talking about a max heap, I'll talk about that in a minute again, a max heap, I know that all my descendants to the left and to the right are less than me. I'm bigger for every node in the heap. In this heap, every node, every element in this heap, all my descendants are less than me. I'm bigger than everybody. That's in a max heap. It is not a BST. Don't forget, again, one of the biggest booms is it's not a BST. I can have to the right or to the left larger or, it's not a BST where it has to be smaller and greater. No, I can have different values, but they all have to be less than me. It's not a BST. One of the common mistakes. So, how do we do it? And what was lovely here? No pointers, no thing. Everything is done in an array. We're going to start, because it's an almost complete tree, we start filling up our heap according to levels. You know, this is number 1, A1, A2, A3, A4. We start filling it up according to levels. You need a new level, continue. Now, we have an array which can contain the heap. So we have the array size, but we also have the heap size. The heap size, in this case, is the same size as the array. But if I delete somebody, so I'll delete it, and the heap size will be 5. The whole array size could be 6. That's fine. That's the maximum of heap size. But the array is my kli kibul, where I can keep the heap. Okay, so we have this heap. Great. So what happens? We know that the max heap, the root of the heap is an A1. We know how to get to its left son and the right son by the left of anybody of I is 2I, the right is 2I plus 2I plus 1. The parent is the floor of I divided by 2. Very easy to work with. How do I get to the left and to the right? I just use playing with indexes. Everything's in place here inside the array. Great. So the maximum in a max heap is A1. We also saw that there's a concept called a min heap. Always check if you took any questions you have in an exam, or when you're building an algorithm, check, do you need a min heap or a max heap? A min heap means that all the values, all my descendants are bigger than me. No problem, all the descendants are bigger than me. That's a min heap, a max heap. So in a max heap, the largest number is here. In a min heap, the smallest number is here. Great. So then we saw the whole idea of a heap insert. How do you insert a new value? Here's my heap, here's my array, the 26 is going to go, the 26 is going to go here. The 26 has to go here into the new value. That's the place, right? Get to the right son of 4. But it's not the correct place. I have to start going up. I have to start floating it up and putting it in its place. So in the end result, the 26 has to become the left son of 28. But as long as my parent is smaller than me, I still have to float up. I'm going to continue floating up like that until my parent's bigger than me. He's bigger than me? Yalla, that's my place. I know my place. And therefore, this is the heap insert. You have the algorithm for it. And the heap insert algorithm, complexity is log n. Because in the worst case, I have to go all the way up to the top. We know the height of a heap is log n. Great. Come on. Now, how do I build a heap? How do I build a binary heap? How do I build this heap? 2 different ways. I can do insertions or using heapify. Using insertions basically says, okay, at first, here's my array. I want to build this, take this array and build a heap out of it. How do I do that? Okay, so I'll say, okay, great. The first value, heap size is 1. So here's my array, but my heap sitting here, just here, This green one, this 28, is my heap. And now I'm going to take every single value afterwards. Every single value afterwards. What am I going to do now? I'm going to insert AI into my heap. So this becomes my heap now. So it says size 2. Heap insert and makes my heap size +1. It increases the heap size. And then puts it in. And now here 32 comes. And again, the 32 become, oh, it's the biggest number. It comes all the way here. I'm going to do the heap insert algorithm. And how many times am I doing heap insert? I'm doing heap insert n times. And heap insert costs me log n. And it's going to cost me n log n. Great. The other way of doing it is using heapify. And we saw the whole concept of heapify is where, first of all, I'm going to say my heap size is the whole size of the array. Great. That's what we want. And now I'm going to go from halfway. I'm only going to have to deal with half of the values all the way to the beginning. I'm going to do a max heapify of AI. Now, what's a max heapify? A max heapify was a great idea where we're going to take that value and we're going to start sifting it down. We'll take it and start bringing it down to where it belongs. And we saw the whole concept. Okay, here's the thing. Start taking it down until you find its place. Okay, so how does that heapify help us? We saw that when we're doing that, we saw a whole way of understanding what is the complexity. And we started seeing that how much it's going to cost us, how many times, what's the height each time, if they're heapified or not. Because theoretically, if you think about it, if I'm only doing half of it because half of them are already heapified. Or less, more and more are heapified according to the height. So therefore, we saw the whole analysis, how we got to it, and it is O of n. It's going to be the complexity of using heapify is O of n. So we have two different ways of building this heap, one using O of n, one using O of log of n. And then we saw the seventh way of sorting. Yes, that's the next thing. Oh, no, sorry. Yeah. And we saw two different uses of heaps. The first one was a priority queue. What's the idea of the priority queue? Is that it's a queue where it's a normal queue when we're inserting. Right? The last guy, yeah, who's last? Yeah, you're after me. I'm after you. Great. The deletion is according to the guy with the highest priority. If there are two people with the same priority, it's according to the order that they came. That's the idea of a priority queue. It's a queue, but there's people with higher priorities. We saw different examples of use of it. It's used a lot in computers and different algorithms. And again, a heap will help me because if I keep my queue as a max heap, if I want to remove the guy with the highest priority, that is the max heap. It's going to cost me O of 1 to remove it, to know who it is. And then I have to heapify the, I have to do a heapify, and it's going to cost me log of n to do the deletion. Great, that was a priority queue. Then we saw heap sort. Very good. What's a heap sort? The heap sort is gewaldig. Basically, it says like this. Okay, what's a heap sort? You have a heap. Here's my array A. Build a heap. Cost me O of n. We saw that. And now I can say like this. Great. Take it's sort. I built a heap. I built my heap, a max heap. So A1 is the biggest number. Put it at the end of the array and shorten the heap. Reduce the size of the heap by 1. Then take the max heap again and put it. And shorten. And this is what you see here. That's the algorithm. And we're sorting our array using the concept of a max heap. And it's going to cost us n log n. Okay. So then we started looking. That was the seventh one. The seventh sort method. And then we got to the last topic. And how are we doing for time? I want to be able to finish on time. Okay, so then we started talking about comparison sorts. The comparison sorts, we saw that we have ones that run in n squared and ones that run in n log n. Again, quicksort runs in n log n in the average case. which is the expected case. We're expecting that, and that's called the expected case. Now, we started seeing that we have something called a decision tree, which can show us what are the comparisons. Why are they called comparison sorts? Because they have to compare all the values one against the other in some way or other, depending on the algorithm. So what happens is that if we see all the different permutations, if I have three numbers, A, B, and C, I have 6 different ways that the numbers can be sorted. So I have, according to the questions, I can get to 6 unique different combinations, permutations. So this idea of the decision tree, so we looked, okay, the decision tree, what is the height of this decision tree? So then we saw the depth, the height of that decision tree. We saw how we got to it. We're not going to go into it now. Is n log n, omega of n log n. Means the height, the depth of a decision tree will never be less than n log n. There's no way that you can build a tree which the height is depth. Yeah, let's call it depth. The depth is n log n. And we proved it. Okay. So if we prove that, how does that help us? Then that means that, and here's the whole explanation, 105. And okay, great, the whole explanation. So basically it means that we need to do n log n comparisons. Because that's the amount, that's the height. Is n log n? So we need to do n log n comparisons. Therefore, I can say very clearly, any sorting that has to be, which is based on comparison, in the worst case, obviously in the best case it could be less. In the worst case, the lower bound is n log n. But you can never build a comparison sort, a sort that's based on comparisons, that in the worst case will run faster than n log n. That is the bottom, that is the omega, that's the lower bound. And you can never build one if it's based on comparisons. Okay, then we saw two concepts in sorting methods, which we talked about, but now the time to finalize it, is about stable. What is a stable sort? A stable sort means that if I have the same value twice, like here, the green and the purple, if the green is before the purple, a stable sort will make sure that the green is still before the purple. But in a non-stable sort, it could be, and there are quite a few non-stable sorts, that the purple will be before the green. Sometimes, as I say in Hebrew, machpat, it makes no difference to me if it's stable or not. Sometimes it's very important, just like we saw in Redic sort, that we need it to be a stable sort. Okay, so we know that. And here, hello, yes, this way. So we saw the different types of sorts, all the 7 that we know. Are they stable or not? The binary sort is stable as long as greater than or equal to the right. Okay, so we have all the different sorting methods, if they're stable or not. The other concept that we saw was in place. Doesn't use extra memory. The idea of in place doesn't use extra memory. Bubble sort, all those don't. And merge sort and binary sort use extra memory. Merge sort builds these temporary arrays. Binary sort, as we saw, builds a BST to do it. Heap sort, obviously, is inside the array, not a problem. And then we saw, in the end, 3 different linear sorts. All the sorts that we saw, all the 7 sorts that we saw, were based on keys, any key. If it's decimal numbers, whole numbers, strings, whatever, it will work. Linear sorts are cool, and they'll run usually in a linear time, but very dependent on the key. The key has to be a very specific type of key. We saw 3 different types. We saw counting sort. The idea of a counting sort that, first of all, the numbers are between 0 and k, between 0 and k, and it uses additional memory. We saw the whole thing, how it works, and this is the algorithm, how we count, and then we do the cumulative. Really cool, really nice. I remind you, the complexity of count sort is theta of n plus k. That is the complexity. It's not theta of n, it's n plus k. But if we know that k, right, the number of values will be less than or equal to n, then it's kilo n plus n will be theta of n. Meaning, for example, let's say I have grades. Okay, I want to sort these grades. The grades are between 0 and 100, and I have 1,000 students. Fine, great. So K is bounded by N, so it will be theta of N. But if my K, like we saw in examples, if K is N squared, then obviously it will be theta of N plus N squared, which is N squared. But so therefore, don't forget, counting sort is theta of N plus K. Then we saw radix sort, the idea of where I'm going to go from the LSD, I'm going to go from the least significant digit and sort it. We saw the whole thing, it's lovely. And it basically uses as an internal, it's a wrapper that uses another sort, its own internal sort, to sort according to the digit, and it uses a stable sort, and therefore it will work. Because I'm using a stable sort, it will work. And then we saw how it works. And again, the complexity is D times B plus N. What is D? D is the number of digits. That's my length of the number of digits. And that's important to us to know how many times we're going to do this loop. We're going to do this loop D times. And what's in the loop? We're going to do some type of stable sort. And so therefore, everything after we saw everything, we saw that it's going to cost us D times B plus N. That is the official radix sort. But if we assume that B and D are constants, base, what's your base? 2, 12, 16. That's it. It's going to be a constant, right? The number of digits, how many digits do I have? If we're assuming that the number of digits on the base are constants, then it becomes theta of N. Not always, that's true. Most cases, yes. Well, again, according to what you're dealing with, you see what is the, can I assume that D and B are constants? And the last one that we saw was the bucket sort. The bucket sort, where very important, we're assuming uniform distribution. If I have N values, I have N values between 0 and 1, I'm assuming that the amount of, in the intervals, if I'm going to make N buckets, each bucket's going to get one guy. That's uniformly distributed. As long as we assume this uniform distribution, and we saw how it works with basically making lists, each bucket is a list, and therefore the sorting of that list, of each list in each bucket, is going to cost me much less. And I sort of presented intuitively how it works. It's based on the permutations, and the sorting time of one bucket is O of 2 minus 1 divided by N. And we saw how we got to it. In the end result, O of 2 minus 1 divided by N is 1. So it's theta of N plus theta of N. Akitsu, it becomes theta of N. Again, it assumes this uniform distribution. If I can have a lot of values in one bucket, then it's not going to work. It's going to become much bigger. It can become even N squared, because I'm going to have to sort, or even worse sometimes, I'm going to have to sort that list, and that's going to cost me a lot. So again, we're assuming uniform distribution. And with that, we saw all the different, we finished the komar. So again, let's just sum up what we learned. We talked about the analysis of algorithms. We talked about linear data structures. We talked about recursion. We talked about trees and different types of trees and different forms of trees and heaps and priority queues. Toch gedeze, we saw all different types of sorting methods. And then we went into the sorting methods, and we saw the whole concept of linear sorting methods. This 117 out of 120 is what we did. This is all that we did in this course. A lot. Think about it. Think about that tool chest that we started off when we met together. And I talked to you in the first class. I said, look, you have this tool chest, and we're going to fill it. It's heavy now. We got a lot of stuff there. A lot of stuff. Some stuff you don't know how to use properly yet. You're not sure about the safety of it. Some you're sure how to use it. And again, the idea is you're given a problem, choose which tool or set of tools are appropriate to be able to solve the problem. And that's what you have here. That's what we have. A toolbox full of great ideas. Okay. And one thing additional, don't forget RTQ in all your exams. Read the question, something that we learned in this class. Read the question and answer it. Make sure you answered all the section, all the parts of it. Make sure you did what they asked you. Read the question. Hadran Alecha, Masechet Bivnei Netunim Aleph. And with that, we have finished the summary. So, עד כאן.
שכוח.
Thank you.